Hello and welcome to Hackon Online. On your right-hand side, you have the opportunity to ask questions, so please use that if you have any. It's a pleasure for me to present Harrison. Welcome to Hackon.
Yes, thank you for the introduction. So thanks everybody for joining. My name's Harrison. I'm going to be talking about a project that we had at my company, kind of an internal training project, I guess you could call it, where we reverse engineered a EV charger that's quite common in Norway and sold in a few different countries. A bit about myself. Yep, my name is Harrison. I'm a security consultant at Mnemonic. If you don't know, we're a Norwegian security company, about 300 people now. I work as a penetration tester in the technical risk services department. So I mainly do most of the time I'm working with pen tests for web applications, mobile applications on iOS and Android, and some IoT. And I guess, as you could say in Norwegian, I'm a bit of a potato. I kind of take a mix of stuff here and there, kind of, for example, like what I'm talking about today. And I'm also originally from the US, if you hadn't gathered that already. So what I'm here to talk about today is, like I said, a walkthrough of a hardware security project that we had in my department. So it kind of why we did it. It was sort of like an internal training thing. It was sort of fun and try something new and get some team building, I guess. Then I'm going to also talk about kind of the motivation why we chose to look into an electric vehicle charger at all in the first place. Along the way, I'll kind of mention a few IT or IoT security considerations, things to consider when developing IoT devices, and then some findings that we had with this specific device. And also, this presentation kind of very closely follows a blog post that's available on Mnemonic's website. So I'll have a link at the, or I can share a link at the end of the presentation. But if you have any, if you want to read a bit further into the technical details, just have a look on Mnemonic's website, and it's very closely follows this presentation. So a bit about the motivation, why look into EV chargers at all? There's tons of IoT devices out there. On a high level, it just seemed kind of interesting, to be honest. There wasn't a ton of public research in the field. EV chargers and EVs are kind of relatively new. I mean, they've been around for a while, but they're just kind of, the infrastructure starting to get built out, and there wasn't a huge amount of public research in the area. At least it seems so to us. It's something that society relies on, at least heavily. Here in Oslo, you have, it's almost synonymous with, kind of filling up your car at a gas station. And I think most people would agree that if all the gas stations stopped working, it'd be pretty bad. So when you start to think about IoT connected devices, that, if something breaks and goes down, kind of has a big impact. So it'd be interesting to see the security behind it and make sure they're, secured properly. Like I mentioned, it's a relatively new market, and it's made by companies that also don't have a really long history of producing devices. So it's not like Google or Apple or Amazon, where they, have a really strong history with producing these devices. So, when you're new, you're maybe not as mature and could potentially, mess up in more areas. So we thought EV chargers would be interesting to look into, and we eventually landed on the Zaptec Pro. So there's a lot of different chargers out there, but the Zaptec Pro is one of the most prevalent car chargers in Norway, at least. And that's specifically for the larger the Pro model. I actually have a slide on it next, but essentially the Pro model is for like networked large installations where you'd have in a parking garage or in a apartment complex or something like that. You also have a home model. And the Pro model had some more functionality for that, networking, so that they can kind of communicate with each other in a single installation. And it also checked a lot of boxes in terms of functionality. You have Bluetooth Low Energy, Wi-Fi, a 4G connection, a PLC, which is essentially Ethernet over power cables. It's essentially the same thing as like Ethernet over power line extender that you might buy for your home if you want to your Wi-Fi doesn't reach, but you want to kind of have two Ethernet connections. And we knew that it ran Linux, so it kind of checked all the fun boxes, and there was a lot of places to potentially mess up. And it's also what we had in the basement at work, so something we were somewhat familiar with. Yeah, so a lot of companies kind of have this seem to follow this similar pattern where you have this version for home, and you have a version that's designed for enterprise. You can see there's a pretty big price difference between the two. But we also thought that more chances to mess up if you have more functionality, and then the Pro version has more functionality. And also the impact could be a bit greater. If you can, for example, get free charging from public infrastructure, like a parking garage, for example, it's a bit more exciting than driving up to somebody's driveway where you could probably just plug in and there's no authentication to begin with. Yes. So kind of like before I really dig deep, just to give a high level architecture about how a lot of these systems tend to work, is that as a end user, a consumer or a customer, you're going to have an Easy Park app or the Fortum Charge and Drive app or some kind of app on your phone that you use when you park your car to start a charging session. That talks up to their infrastructure, and then you have Zaptec and you have other companies that have charging hardware as well. So generally, what happens is you have the infrastructure for the Easy Park and Fortum. They're going to integrate with various different providers. So in this case, you can see they Zaptec talks to Easy Park and Fortum, and when I click start charging, it goes through the cloud and it comes back down. I guess the arrows technically go both ways, but that's kind of the high level communication flow. So digging a bit into how to think about conducting or how we thought about conducting a hardware security assessment. Most good security assessments are going to start with reconnaissance. So this is even before we bought anything. We kind of wanted to poke around and kind of understand how the device was built. So just going to Zaptec's website and Google, we found a lot of information. They had a lot of actually really good documentation and public information. There was Swagger API documentation for how to integrate with their systems. So basically what Easy Park and Fortum would be reading so that they could kind of integrate with the Zaptec's backend. We found links to portals where if you're a system integrator or an installer, you can kind of manage your installation. There was a lot of marketing material, and one of the screenshots on the bottom there, they even have data flows and request flows. So you can basically you can learn a lot without even having to get the device or have access to one. Another thing, kind of along that stage, I just kind of a side note, something I personally really like to look into in reconnaissance is certificate transparency logs. So essentially, what this is a list of all of the certificates that have been issued for a domain by a public certificate authority. So essentially, there is a regulation or some kind of, I don't know what to call it, but some kind of rule from all of the certificate authorities where whenever they issue a certificate, they have to kind of publish that publicly saying, hey, I'm Let's Encrypt, for example, and I've issued a certificate for this domain. And then there's services like crt.sh that kind of index all of that. So effectively what you can do is type in a domain like zaptec.com, and you'll get a list of all of the domains that they've issued certificates for. Sometimes they're not connected to the internet or they're old, but literally just kind of going through saying, okay, this domain might exist, copying it and pasting. It's a nice, easy way to kind of map out what kind of services they might have. Another really good place to look is if they have any mobile applications. So I think Zaptec actually had 2 mobile applications, at least for Android. They had this app that you can see in the screenshot here. And I think they had another app. I don't remember off the top of my head exactly what it was. So even before we bought the device, we installed the app. We were able to create an account and play around. It's mainly seems to be designed for home users so that they can kind of manage their own device, but it also has a sort of hidden but not really functionality for system installers. So even before we got the device, we were able to kind of enter into this functionality and get an idea about if I were a professional, electric vehicle charger installer, what does that process look like? How do I onboard those devices and get them all kind of networked and connected together? So just using the app is a really good source of information. We were also, most Android applications are it's quite simple to decompile them. So you can get the APK file and throw it at a decompiler like JADX, and it will try its best to kind of go back to Java code. It's a bit, it's not one-to-one, it's a bit messy, but you can sort of make your way through, even if it is obfuscated. So their code was, they had applied some obfuscation to it. You can see on the left-hand side, it's just a bunch of, AC. They had all these classes and methods that just got renamed to basically garbage. But there's still some things that they're not able to change. So for example, in this screenshot, it's kind of defining, we were able to find the part of the code that defined all of the Bluetooth characteristics. So essentially, like with the Bluetooth Low Energy functionality, like all of the different functions that you could do from within that, if that makes sense. So even before we got the charger, we could kind of see what functionality it might have over Bluetooth Low Energy. So certainly interesting. So the fun part, we bought a device. Getting the Pro model was actually easier than we thought it would be. We just walked up to a store, actually a physical store in Oslo, and said, "Hey, can we get a Pro device?" And they looked at me a bit funny, and they was like, "Sure, whatever," and they sold it to us. Yeah, so we bought it, took it back to the office. We did look into it a bit before we decided to start unscrewing things. We tried to connect it to the network, but we were actually a bit limited in what we could do because we weren't Zaptec for their professional devices. You need to be a registered installer so you can get access to this like onboarding portal. And obviously we're not authorized to have access to that portal. So basically using the mobile app, all we could do is kind of connect it to Wi-Fi, run a port scan. We realized that it had SSH listening. We couldn't seem to log in with any, super obvious credentials. We also did some packet captures and saw that it was talking up to Azure IoT hub for its communication, but that's about all we could find out. So pretty quickly, we just started taking it apart and started poking around and looking at basically what you see here. So after you get access to the hardware and kind of like a good way to think about a hardware security assessment in general is to really kind of get a lay of the land and kind of get your bearings on what's going on. And a lot of the times it's, you can sort of, eventually if you look into it, you can sort of see some organization going on. So you can see in the picture here, there's two PCBs, there's two circuit boards. On the bottom, you have a lot of the high voltage stuff. So you have some, relays that are in those black boxes, and you have those big wires coming out for the kind of switching the voltage on and off. And then you have this daughter board kind of sitting above it that's connected through this, header on the bottom left. And that's where most of the interesting IoT stuff was happening. So you can kind of see the separation. So we never even looked into the power side of things. Didn't seem terribly interesting. So we placed our focus on the IoT board. Zooming in there a bit more. Oh, yeah. Okay. So I guess I can talk about that too. So essentially what you're going to do is start, like after you kind of find your initial target, you can kind of basically just look at the serial numbers on the chips and start Googling. I have some boxes here. So we Googled, and in the top right, you have the 4G modem and a 4G antenna. So like, okay, so like this part of the board seems to be 4G related. You have in blue on the left-hand side, you have like an RFID antenna. And if you Google the part number for that little black box above that, it's comes up as a RFID reading chip. In the bottom right, you have a microcontroller. It was kind of generic. Didn't actually look too much into that during our assessment. Basically because we knew that more interesting stuff was going on, and the microcontroller just simply didn't have enough processing power to really handle the internet connectivity, all that kind of stuff. And that's where we wanted to place our focus. In orange is the kind of the power line connectivity functionality that I talked about earlier. So kind of, sending, Ethernet over power cables. And then finally, the most interesting part is what I have highlighted in red. So moving from right to left, you have from left to right, you have a NAND storage flash chip. So kind of like the hard drive. You have in the middle that comes up as an ARM processor, sort of similar to what you would find in a Raspberry Pi. And then on the right-hand side, you have memory or RAM. You may have also noticed that there's 3 pins to the very left. Something you kind of want to keep an eye out for is debug interfaces. Debug interfaces often, are kind of a gateway into learning more about the device. It could be a serial interface, where you could kind of, get a console and see the logs from a device as it's booting. It could be a JTAG interface, which could potentially, if it's enabled, let you dump the firmware, which could let you see what's going on inside the file system. So basically kind of keep an eye out for that as you're going along. So there's, we did see 3 pins that was located close to the processor. So that was certainly interesting to kind of pay attention to. So zooming in a bit more, those pins I was talking about, kind of using the process of elimination to find out what they were. If you know much about PCBs, you can kind of already, just based on looking at it, see that the bottommost, or kind of towards the left side, is a ground pin, because it has 3 little arms kind of connecting out to the ground plane on the PCB. So I know that's a ground connection. And then you have 2 other connections, which are probably data lines. Basically, we figured that it was probably a serial connection, or what's it called? Or SWD connection, which is like a debug interface for ARM, because they both use ground plus two data pins. Yes. So yeah, so we the next step was kind of to solder a connection onto those data pins and kind of just see what it was doing. So not really sending anything just yet, but what we did was we had a logic analyzer. you can get them pretty cheap online, and basically just turned it on and checked to see if it was sending out any data. We using the logic analyzer, we found out that it was sending, it was a serial connection or UART, and it was the console for the the ARM processor. So basically, when you turn it on, you could see all of the Linux startup logs, and when it finished booting, it dropped you into a login prompt. And so we did actually, we tried and I think let it run for a day, brute forcing some common credentials with no luck. And I'll explain a bit why that happened later on. Yeah. Oh, another point as well. One attack vector that we tried here before digging deeper is attacks against the bootloader. So essentially what happens is kind of like when you turn the device on, you get, first you hit the bootloader, sort of like the BIOS or grub. For a lot of embedded devices, it's tends to be U-boot, which is an open source bootloader. And so sometimes if you can get into the, that has its own kind of console that you can get access to. And if you can get access to the U-boot console, sometimes you can get access to dump the firmware or change the startup parameters that get passed to the Linux installation. And you can kind of sometimes bypass logins and do all kinds of stuff from there. But Zaptec looks like they did their homework or got lucky, and we weren't able to kind of exploit that either. So we were sort of hit a dead end after we connected to the to this serial interface, other than gaining a lot of information. Obviously, the logs contained a lot of interesting information about how the device worked for later on. So here's a photo of like I was saying, we soldered some pins onto those three headers, and that's how we got the output that I showed in the last screenshot. This was also about the same time when we realized that that little silver rectangle was about the same size as a SD card slot. So I thought, yeah, when I initially looked at it, I thought it was some kind of debug interface, but I had no idea what it was. And I just happened to have an SD card sitting next to me, or micro SD card. And I was like, this looks super similar. So I just plugged it in and checked to see what it would do. I rebooted it and got nothing back out of the serial console. So kind of figured one of two things here. Either we really screwed up and broke the entire device, or it was trying to actually use this SD card as a boot device. And obviously it was not configured with any sort of software to boot from. So it failed and it just kind of hung. So we dug around for a lot of documentation kind of related to this ARM processor. And it did seem that it was quite normal for for this processor to kind of have an SD card as a boot device, sort of like just like a Raspberry Pi, to be honest. And there were some other development boards that there was public firmware released for that was compatible with this. It had the same processor. So essentially, what we thought was, okay, the interesting stuff that we want to get access to, the goal here would be to, one, get root, but two, even before that, it'd be really nice to get the software that's running on the charger. So I want to be able to kind of read that NAND flash chip. So essentially, like the same concept of, you have a laptop and you have a hard drive. Assuming it's not encrypted, you can boot to a bootable Linux disk and kind of dump the firmware. So we were trying to find different firmwares that were compatible, that we could boot to and potentially access this NAND flash. We tried a bunch and none of them worked. Ultimately, this was down to hardware differences, because this is a custom PCB. This is a custom board that's been developed by Zaptec, and the way that the all the different hardware components, kind of like the operating system needs to be built specifically, saying with needs to be built with keeping in mind, like, the RAM is connected to these pins, and I'm using this specific chipset for the NAND flash, and basically kind of all the different components can be configured differently depending on how they've developed the board. So I think the issues that we were running into is that when the processor started to boot off of those, the firmware that we gave it, that we found online, the just stuff was connected to different pins, and it was expecting different hardware. So it failed. So yeah, we weren't able to take that route. So we had to kind of crank it up a notch and go to the next step, which was to physically desolder the NAND flash storage. So we don't have a very great setup for this, but essentially just used a hot air soldering station that we got from AliExpress. It was probably like $50 or somewhere around there, not too expensive. And you kind of just blow hot air onto the chip until it gets hot enough to melt all the solder, and then you can kind of pop it off. The reason you can't really use a normal traditional soldering pen here is that you can only heat up a few pins at a time, and the chip won't release because the other pins will be holding it down. So you kind of need to heat it up evenly so it all pops up. You can see my soldering skills aren't 10 out of 10. I melted the plastic pins a bit on the left and scraped the PCB when I was lifting the chip, but all in all, it was okay. Not too much damage was made. A tip, if any of you attempt this in the future, there's something called Kapton tape, which is like this orange tape. You can get it at, you can buy it online or at Shell and Company. And you can kind of, it's a heat shielding tape. So you can kind of place it around all the other components you don't want to get hot. I've done some of this before, and you can kind of see in this photo, there's some capacitors, some really small capacitors right next to the chip you're trying to remove. And if you don't put that tape down, there's a high likelihood that you're going to melt the solder on those as well. And, it is a hot air gun blowing air at a decent amount of speed. And those will, if the solder melts, you have a high chance that they'll just blow away, and you'll kind of destroy your board because you're never going to be able to find them or know how to put them back. So yeah, we popped off that NAND flash chip and put it into another cheap AliExpress device, a chip reader. So essentially the chip popped off, and it has this, we got this socket for the specific size, popped it in, and then used some sketchy software to dump the flash. So after this, the program output, essentially just a big binary file, just a raw dump out of the flash. So next, we needed to start kind of taking that binary file and wanted to get something meaningful out of it. Normally, NAND flash, so that flash chip, it requires a controller. Essentially what you have is NAND flash by itself is not terribly reliable. So you normally have a controller that sits in front before the operating system sees it. And that controller kind of takes care of what's called out of band data. So, you have this extra reserved space in the NAND flash for wear leveling and error correction. So there's kind of like error correction bits in case something is messed up on the NAND chip, so that the controller will kind of automatically fix that. And it tries to do some level of wear leveling. So if it detects that a bit is bad, there's some reserved space for it to get fixed. So the problem here is I stole this slide from actually a talk that was done at Hack the Box Amsterdam in 2019. I can. There's actually a link in the blog post if you guys want to check that out. It's pretty good. So essentially, the issue here is if I wanted to analyze this flash jump that came from the NAND chip directly, it's just in between. You kind of have all this out of band data, so it's all chopped up, and you're going to get a bunch of garbage. So that needs to get fixed. So really thankful to the guys that kind of worked on this tooling to kind of clean up this data. they released this tool that you can see here, which essentially just allows you to give it that raw dump from the NAND flash chip, and it will kind of remove all of that out of band data. And they even have some cool functionality where it'll even it implements the error correction. So like if there was actually a bad bad bit or something, it'll kind of apply the error correction that just like the controller would have done. So that was really helpful. Yeah. So at this point, we were able to, after we had the flash image, we could kind of start analyzing it like you would a normal, binary flash image. And a few different ways you can kind of go about this. But essentially what we ended up doing was emulating a NAND flash device, sort of like a virtual flash device in Linux. There's some commands you can do that. And then we formatted it with the image that we got as output from this tool. And then we mounted it. And then we kind of sat with essentially like in Linux, so like /mount/ NAND, for example. And then we could kind of see like all of the folders that you would have in a Linux installation, just like normal, like, etc home and lib and all that kind of stuff. So basically now we could access the file system for the charger. So still wanting to be able to get root on a running device. And we hadn't been able to do that so far. So what we did was carve out what's called the device tree binary. So essentially like what this is like I said before, how every board is different, and could use different RAM chips or memory or NAND flash, and everything's kind of connected to different pins. Essentially this device tree binary is a blob that sort of describes what's connected to what. So we extracted that from the NAND flash that we just dumped with this tool, and plugged that into a essentially like the build process for U-boot. So we built our own bootloader that had a bunch of that we specifically turned on a lot of debug functionality for, and which allowed us to burn that bootloader to the SD card, because we knew earlier that if we put an SD card in with the right stuff, it would try and boot. So we got it to boot to our specific bootloader, and then we were able to. You can see towards the end of the screenshot, you can see the boot arguments that get passed to Linux. So what we did towards the end, it's a bit hard to see, it's a big mess, but you can see the single init bin bash. So essentially what that does is in Linux, if you pass it this command, it won't prompt you for password authentication, and it'll just drop you into a root shell. So quite handy. So what we did was we booted into a root prompt, changed the password to something that we knew, and then we got turned on the device and connected to it via SSH. So now we had root on a running device. From this point, it's really nice because we can analyze a running device and see what it's doing. So the first thing we wanted to look into was the Bluetooth low energy. Personally, I think it's quite an interesting area. It's basically BLE is honestly everywhere. It is separate. It's a separate technology from traditional Bluetooth, but they are often kind of talked about in the same place. So anytime like electric scooters or the automatic mailboxes where you kind of puck a box or whatever, where you go up and push a button and the door opens, and car keys for like the Tesla, where you walk up to the car and it just unlocks. This is all over BLE. And generally authentication with BLE kind of sucks because a lot of the times the developers want to avoid pairing. So they kind of implement their own weird authentication solutions. So in the case of Zaptec, they didn't want you to have to like go into your Bluetooth settings and pair the device. So they implemented this like 4-digit PIN code system. So we had some questions about how that worked. We wanted to know how was the pin generated? It's just 4 digits. Could you brute force it? Is there a way to derive it from something? And then if you do get the pin code, what can you do with that? So yeah, digging around in the file system that we had access to now, they actually left some provisioning logs from when the device got provisioned at the factory. So you have some timestamps, and you can, it was literally in the log folder of Linux, and we found on one of the lines that says got provisioning data, and that's the serial number. And then what I blacked out was kind of a key for the cloud communication, and the pin code that we got. So at least it wasn't derived from something on the device like a MAC address, which some other devices do. So it seemed if it's coming from a provisioning server in the factory, hoping that it's unique, that's it's not the worst thing in the world, at least. We were also able to poke around on the code to see what functionality the device implemented over Bluetooth Low Energy. So you can see on the right-hand side, we have a list. Actually, this is from the app, from the mobile app, so we could have had this before. But we also looked at the it was running .NET on the charger, so we could see that as well. Some issues you could potentially have with BLE is that it's not encrypted by default. Most people don't encrypt. So technically, if you were there at the right place, right time with the technician, you could sniff that pin code. The pin code is printed on the box. So if you had access to the box, you could potentially get the pin code. And there doesn't seem to be any end user functionality to actually change it. So a few potential issues there. And maybe a bit out of order, but here's the BLE code that we found running on the charger itself. Some of it was written in .NET and some of it was written in Python. Python is quite nice because it wasn't compiled and it had all the comments and it was easy to read. We found one functionality called run command, which seemed pretty interesting. Wanted to dig into that a bit. The command itself, so the Bluetooth interface is managed by Python. And then it kind of passes the content of that command over to some .NET code over a dbus interface. So we kind of followed the breadcrumbs and disassembled the .NET. Essentially what we found out here is that the only commands that this Bluetooth functionality had would really be to restart the charger or request the charger to check for a firmware update. So even though it said run commands, it didn't seem terribly useful. We thought maybe there were some hints on the mobile app that it would have been possible to start a charging session over Bluetooth. But that didn't seem to be implemented on the charger. So kind of a dead end here. We didn't look into everything, but on a surface level, at least this functionality didn't seem to have anything terribly wrong with it. We also took a look at the SSH listener and the root password. Obviously, before we tried to try some common credentials when we were sitting at the authentication prompt. We found out why we weren't able to authenticate. Essentially, there was no password authentication enabled. So we went into the Etsy shadow file, and it was completely empty. So essentially, that disables password-based authentication. The device did, however, have some public SSH keys provisioned with it. So presumably Zaptec could use these. They have the private key, so they could authenticate over SSH to the device. So that seemed to be okay, at least, or not terrible. The third kind of area that we briefly looked into was the cloud connectivity. Once we had root, that allowed us to install our custom certificate so that we could man in the middle of the traffic. We used Midem proxy to do that, to intercept the TLS. And then we viewed the data in Wireshark. We found out that, as we thought before, based on the PCAP, it was talking to Azure IoT Hub, which is the MQTT-based protocol, and they authenticate to Azure with a shared access signature using a key that's provisioned along with the PIN code from when the device is at the factory. So this seemed to be quite standard, not too bad. Just out of curiosity, or just kind of thought it was interesting, here's some of the data that we saw in Wireshark. So, there was this uses, this is a message where the device is kind of sending up to the cloud, some of the usage information, like how many kilowatts have been used. We also found some, this is over the cloud communication. We found some debug functionality that Zaptec can use to kind of remotely control their devices. Looks a bit scary, and maybe they could have potentially found a better way to do this, but it is pretty standard. I mean, if you think like Google and Apple and Amazon, all, I can guarantee, have ways to remotely manage their device, just like Zaptec. But yeah, so we basically found here where they can send a command up to the cloud, which will directly execute commands in Linux. They also had some functionality sitting alongside this where they can actually start a reverse shell where they'll get the device to reach up to a listener that's in the cloud. Yeah, so that's kind of interesting. It actually, they actually do have a private key that's stored on the device that's used for communicating up to the cloud, but the host name is defined every single time they run the command. So it's a bit hard to exploit unless you know exactly if you're at the right place, right time, and know what server they're trying to connect up to. So overall, the device, not bad. Much better, to be honest, than a lot of IoT devices that are out there. I didn't really expect the same level as the major hardware manufacturers. So for a medium-sized company based out of Norway, not too bad. They could have implemented secure boot, which would have prevented us from running our own firmware. It is supported by the processor, just needs to be enabled. They could have encrypted the firmware. That would have stopped us from dumping the NAND flash and being able to see the software. They could have also disabled the serial interfaces, and they could have also disabled the SD card interface. It would have made our job a lot harder to kind of do what we did. So, yeah, there was also a lot that we didn't dig into. This is kind of just like, it was mainly just for the purpose of playing around and seeing what we could do. We just touched on a few of the most critical areas, if that makes sense. But yeah, definitely, if somebody wanted to pick this up, I can guarantee there's a lot more to look into. So that's all I have. Want to say thanks. My contact information is there on the bottom left. You can email me, harrison@mnemonic.no, and my Twitter is @hsant. And I'll check out the questions here if anybody has any.